Hello and welcome. My name is Radu Hobinku. I am an assistant professor with the University Polytechnica of Bucharest, and I'm here to make this presentation about a relatively new master program offered by Department of Electronic Devices, Circuits and Architectures named Advanced Computing in Embedded Systems. It was first added to our educational offer in 2018 by a team of professors from the Computing Architectures group in order to tackle a specific field which we identified as not being properly addressed in our university. As a complement to the high-performance computing field that is very well taught by our colleagues from the Faculty of Automatic Control and Computers, the field of computing in embedded systems targets low-power, high-efficiency computing for a large field of applications. This field covers automotive applications, Internet of Things, wireless sensor networks, smart portable devices, as well as a wide range of application-specific systems. Since 2020, our group has begun collaborating with the European Centre of Nuclear Research by contributing to the ATLAS experiment with software and FPGA design know-how. Following that effort, we now have 5 of our current master students and alumni as research assistants developing hardware and software for the ATLAS experiment. In order to gain experience in developing such systems, in this master program, you can learn and acquire many skills in software development targeting embedded systems, FPGA system design for accelerating and offloading computing-intensive tasks, as well as parallel and GPU programming for cloud computing. In the following slides, I will quickly go through the master topics. The first semester introduces a few base subjects in order to familiarize the students with the field. The most important building block for embedded systems is the microcontroller. This subject teaches students how to use microcontrollers, describing the features present in all mainstream models, instruction sets, memory organization, interfaces, security, and others. Applications are using ARM processors as well as the open source RISC-V architectures. Since embedded systems go-to operating system is Linux, the subject presents its main features: kernel features, user space and driver development, resource and process management, shell interpreter syntax, inter-process communication, and services configuration. Our faculty is a member of Red Hat Academy, so our students have free access to Red Hat System Administrator courses, as well as a discount for the certification exam costs. Functional verification is required for digital systems engineers in order to properly test their designs. It covers test planning, technologies, methodologies, and languages specifically designed for improving the testing process. The course contents have been developed in collaboration with our partners from AMIC Consulting and Tremend. Another hot topic in today's world is machine learning, and so it cannot be missing from our curricula. The fundamentals of machine learning and computer vision introduces the theory behind artificial intelligence and presents several well-known deep neural network models with applications in computer vision on embedded devices. The Digital System Design project is the first of a sequence of 2 projects where students will integrate all their knowledge and skills in order to design a computing system using an FPGA board and state-of-the-art design tools and the Verilog hardware description language. The second semester introduces advanced topics in both software and digital design. The evaluation of all these subjects is done through an integrative project that requires the students to optimize a piece of software using performance analysis and optimization techniques, and then identifying bottlenecks and offloading intensive sections to FPGA cores. Meanwhile, students are encouraged to use best practice approaches in team development using a revision control system, keeping track of issues and bugs, creating complex build systems, setting up continuous integration processes in software containers, and generating comprehensive and useful documentation. Reconfigurable computing presents the newest and up-to-date design flows in digital design using high-level synthesis tools like Vivado HLS, generating IP cores and interfacing them to the software layer using ACES buses and Python libraries. This is practiced in Xilinx Pink Z2 boards employing Zinc family SoCs. Performance analysis and optimization handles techniques to analyze and profile software applications, as well as several methods to accelerate runtime execution by using parallelism, intrinsics, and algorithm optimizations, as well as reducing code size for low-sized program memory. Software development process and testing covers everything engineers need to know about writing code. Course starts with Git revision control system, continuing with GitLab platform features, GNU Make and CMake build systems, unit testing, documentation generation, and finishes with advanced C++ features. Digital System Design 2 continues on the work from the previous project and finalizes a complete system, integrating the processing core with the rest of the peripherals. Starting with 2021, this project will also involve FIN, a Xilinx experimental framework to deploy torch neural network models on a ping board. While the level of software abstraction has increased steadily over the years, having now access to cloud computing and microservices, software engineers will slowly abandon the compilers and formal languages field, leaving hardware engineers to pick up the slack. In the embedded environment, having access to reconfigurable systems means we can also reconfigure a processor instruction set. While this is a clear advantage, it is useless unless the compiler can make use of these new instructions. The compiler's course introduces the LLVM toolchains, teaches the students about the compiler's building blocks, and trains them to change the backend and add optimization passes. This course content was developed by one of our close collaborators from Trement. Distributed and high-performance computing addresses the upper end of a computing system stack. Useful for offloading processing to the cloud, but also for distributing large portions of computing on many low-power, low-performance processing units with low overhead. This course presents many frameworks for distributing computing like MPI and MapReduce while discussing scalability and overhead. This course is designed and taught by a professor from the Faculty of Automatic Control and Computers. While distributing computing among several systems is a good way of accelerating computation, most modern computers, including embedded systems, have massively parallel chips available for intensive tasks. Parallel Computing course introduces CUDA and OpenCL as a way of programming GPUs. It also teaches how to profile and optimize GPU applications. Wireless sensor networks are used in many applications from communication systems to environment monitoring, security, and smart houses. This course discusses most common topologies and introduces several performance metrics when analyzing performance and constraints. The course is designed and taught by one of our colleagues at the Faculty of Automatic Control and Computers. The fourth semester is specifically reserved for developing the dissertation project. We encourage all of our students to write at least one scientific paper in order to publish the results of all the research done during the master studies. Since 2018, our students have published only a small number of 4 papers in EC conferences and journals, but we are hoping that this number will grow in the future. Our growing list of partners can be seen on this slide. We are making efforts to connect to several other companies and universities for long-term collaboration. We are collaborating with Xilinx for research in quantized neural networks, our best students having the opportunity for an internship in Dublin, South Ireland. Our future plans include increasing the scientific output of our students, meaning research papers in journals and international conferences, closely working with CERN to bring more students into the Atlas project, and obtaining funds for scholarships, certifications, conferences, and training of our students, as well as purchasing updated equipment and devices. Thank you for your attention. If you have any questions, you can always email me. The email address is visible on the first slide. We are looking forward to hearing from you and for you to join our master program.